Hello and welcome to API Access Control Strategies Beyond JWT tokens. This talk is about things you should consider when implementing API Access Control with JWT tokens, things that can go wrong, and things how to fix the issues. My name is Judith Kahrer. I'm an identity specialist at Curity with a focus on API security. I'm also one of the authors of the book Cloud Native Data Security with Auth. If you want to dive deep into Auth or learn how to apply Auth in a cloud-native environment, check it out. The book is currently available for free from Curity's website. You will also get a chance to grab a signed copy at Nordic APIs Platform Summit 2025 in Stockholm. With that said, this talk is Auth related, but it focuses on a very specific detail, the access token, that, in my experience, many people don't pay enough attention to when talking about how to secure APIs using Auth, or how to implement token-based access control. A common token-based architecture is an architecture where the client, the application, sends a JWT token to the API. And when I say API, I mean the services that implement the features of the API. The services validate the access token and implement the access control rules. Now, this practice becomes hard to scale. That is, governance and auditing get challenging when there are many services. In this case, you should consider a policy-based approach. In policy-based access control, you pull out the rules from the services and put them into a different document or documents. The policy is decoupled from the services and their development lifecycle. Policies can now have their own lifecycle, including their own testing and versioning. Consequently, policy-based access control provides more agility and central auditing, which improves compliance. The services consult the policy engine for an access control decision and are responsible for enforcing that decision. As part of that, they can forward the access token as an input to the policy evaluation. This works because anyone can use JWT tokens. JWT tokens are just like concert tickets. If you have one, you can enter the event. That's actually also their greatest weakness, because it makes JWT tokens vulnerable to token replay. Token replay means that if a malicious party discovers a bearer token, they can craft their own requests and gain access. Typically, malicious parties try to change the context in which the access token is used to collect as much data as possible. Token replay thus implies a data breach that can include intellectual property, customer data, data from business partners, and much more. Data breaches are expensive. To mitigate this risk, use a different type of token, a so-called sender-constrained token. Sender-constrained tokens, or proof-of-possession tokens, are tokens that are bound to a key. This means they contain the so-called confirmation claim that points to a public key. For this kind of token to be valid, the client, the application, needs to prove that it can control the corresponding private key. When it comes to sender-constrained access tokens, there are two ways for applications to provide that proof. They can either use mutual TLS as defined in RFC 8705 or self-signed JWT as defined in RFC 9449. Mutual TLS, as the name suggests, uses the transport layer. That means the application and the API establish a mutual TLS connection. And for this, the application needs to have a trusted client certificate and the corresponding private key. The access token then points to the client certificate of the mutual TLS connection. Therefore, this type of token is also called certificate-bound access token. When validating a certificate-bound access token, the API retrieves the client certificate from the transport layer and checks whether it matches the key reference in the access token. Certificate-bound access tokens mitigate token replay because the malicious party would need to have a trusted client certificate. It would not only need to have any trusted client certificate, but the application's certificate that the access token refers to. More specifically, the malicious party would need to get hold of the application's private key for the certificate-bound access token to be deemed valid. It is common practice, though, to protect that private key. So getting hold of that key is a completely different challenge than getting hold of an access token. There is a particular challenge with mutual TLS, because mutual TLS is not an end-to-end solution. Mutual TLS typically terminates at the proxy, such as the API gateway, which means services cannot validate the certificate-bound access tokens as they don't have access to the mutual TLS connection and the application's certificate. To solve this issue, you need to implement a workaround. You need to have the API key extract the certificate from the mutual TLS connection and forward it to upstream services, for example, in a custom header. In this way, the services can verify the key binding in their certificate-bound access token. One of the big benefits of mutual TLS is that the protocol is widely supported. In addition to that, certificates can be third-party assertions, which enables accreditation. This means there can be an authority that only issues certificates to compliant clients that fulfill certain requirements. This is why you often find this solution in regulated ecosystems such as open banking. On top of that, mutual TLS provides built-in authentication. On the other hand, mutual TLS requires a public key infrastructure that comes with complex operations, including the workaround for TLS termination. You need to be able to roll out certificates to the applications, which is not always feasible, such as for mobile applications or browser-based applications. Therefore, there is a different solution called demonstrating proof of possession. Demonstrating proof of possession, short DPoP, uses the application layer. This means the application creates a key pair at runtime. The access token references the application's public key. To prove that it controls the corresponding private key, the application creates a self-signed JWT, the key proof. The application sends both the access token and the key proof to the API. The API gateway can forward the tokens, and as a result, the services have all the information they need to validate the key binding. This means that DPoP provides an end-to-end solution. DPoP mitigates token replay because a malicious party needs to be able to create the key proof to gain access. But since they don't have the private key, they cannot do so. Even if a malicious party had a proof, it would not be able to replay the access token in a new request because the proof is a one-time token that is bound to the original request. The benefits of DPoP are that it's suitable for basically any application, but in particular mobile and browser-based applications. It uses runtime keys and provides an end-to-end solution. However, it comes with more complex validation requirements because services also need to validate the key proof and keep track of whether they have received a proof before. Speaking of validation, there are measures that you can already apply without sender-constrained tokens to reduce the impact of token replay. First of all, have a list of trusted issues. Now, this is a self-evident rule and all the auth libraries support that. It prevents services from accepting access tokens from non-trusted issues. Second, validate the scope. Only accept scopes that the API supports. This prevents services from accepting access tokens with non-supported privileges. Most importantly, validate the audience. The audience claim contains the intended receiver of an access token, the one that should give access to protected resources. Now, what is it actually that needs to be secured? This is an API conference, so one answer is APIs, but technically it's not the APIs that need to be secured, but the data and functions that APIs expose. This means you need to enforce the access control rules wherever data is manipulated or returned. What are those rules? There's not a generally applicable answer to this question because the rules are specific for each organization and business. Of course, there are protocols such as auth or auth-send to support implementations. There are also models like role-based access control, relationship-based access control, or attribute-based access control that help designing policies. No matter the details, there is one thing in common for all rules: the need to know who is requesting which access. In other words, rules need attributes. The rules need to be able to determine the subject, object, and requested action. Identity attributes are used to describe the subject, the who, and this is where JWTs come in. JSON Web Tokens is an encoding format, that is, it defines a standard to package data in a URL-safe, verifiable manner. As a result, JWT access tokens can be used to transport identity data to services, and because JWTs are signed, the services can trust the data in the tokens. JWT access tokens can contain all sorts of data. Some data is technical, like the expiration time. Other data is about the identity, the subject. Some data, for example, the audience claim, is about the resource. Some data, like the scope, is about the action, and some data can be sensitive, which implies a confidentiality risk. Unless encrypted, any party can parse JWT access tokens. Applications may misbehave, have vulnerabilities, parse JWT access tokens, and leak data. Malicious parties may discover an access token and retrieve data from it without ever sending a request. If the access token contains personal information, the data it leaks can also imply a compliance risk due to privacy protection regulations. The solution to this risk is to not use JWT access tokens in the first place. Instead of issuing JWT access tokens to applications, that is, clients, have the authorization server return OAuth tokens. OAuth does not demand any specific token format. This means the access token doesn't have to be a JWT and can be an opaque, non-parsable string. However, JWTs are great for APIs because they are self-contained and thus provide a scalable solution for API access control. So the idea for the improved token-based architecture is to translate the OAuth token to an internal JWT. There are different ways on how to implement that translation. One example is to use token introspection to get the associated data in a JWT format. Another example is to use token exchange to exchange the OAuth token for a JWT. The benefit of this improved architecture is that it builds upon existing standards. It does not require any changes in the application or services. You only need to adapt the authorization server and API gateway. At Curity, we call this approach the phantom token pattern. The benefits of the phantom token pattern, as I said before, is that the changes you need to implement are very local, as they only affect the API gateway and authorization server. The architecture provides confidentiality because it never returns any parsable data to the client or outside of your network. And related to that, it also provides privacy in case of the access token containing personal information. The architecture introduces a trust boundary via token translation. What does that mean? It means that there are two kinds of tokens now, an external access token and an internal JWT. The internal JWT is different from the external access token. Having this boundary mitigates token replay due to supply chain attacks. If an internal service leaks an access token that a malicious party aims to replay at the public interface, the API gateway won't be able to translate that token, and thus token replay will fail. The internal JWT can actually be so different from the external access token that it gets a new name and is called transaction tokens. Transaction tokens are internal JWTs with a very limited lifetime and scope. They can contain details about the request, such as the client's IP or HTTP method or path, in addition to the identity data from the access token. They provide the means to implement least privilege access and zero trust, which leads to a more secure and robust architecture. And speaking of results, I want you to take away 3 main points from this presentation. First of all, enforce access control in the services where data is manipulated or returned. If it gets hard to manage the rules, consider policy-based access control. Second, use sender-constrained access tokens to mitigate token replay. And finally, use JWTs for APIs and OAuth tokens for clients to improve the token-based architecture. Thank you very much.